So our last couple of reactions in this chapter mainly focus around the idea of hydrolysis. So hydrolysis is largely the opposite of what we covered earlier. So we covered our esterification and our amidation. Hydrolysis, which is going to be adding water, will allow us to convert things like esters and amides back to carboxylic acids. And so the net reaction will look something like this. So we're breaking apart that bond and basically doing the reverse of what we saw earlier. Now, when it comes to ester hydrolysis, you can do this under acidic or basic conditions, but it's much more commonly done under basic conditions. There's some factors in the reaction that we won't get into, but the reaction becomes a lot easier to control under basic conditions. And so it really just looks like here's an ester, and we add something like sodium hydroxide to it. And then we typically need a second step. The second step is to just quench with acid. If you don't quench with acid, instead of getting the carboxylic acid as a product, you just end up with a carboxylate salt. But again, your ester gets broken in half, and you form the carboxylic acid, as well as an alcohol. And you can do this for any ester, pretty much regardless of whether it's very simple like the one there, or for ones that are more complicated. Again, we get a carboxylic acid plus an alcohol. Now, one of the most interesting and most important applications of this reaction is where it gets its other name from. This reaction is sometimes referred to as saponification. And that's just a word that means we're making soap. So how do we make soap? Well, if we start with a compound that looks like this, so those R groups there are going to be somewhere on the order of 12 to 20 carbons. And you notice we have 3 of them all attached to these ester groups. And this is known as a triglyceride. And so if you take a triglyceride and add sodium hydroxide to it, you can actually cleave all 3 of these bonds. And then you also get this triol as a byproduct. The triol is glycerol, and glycerol is commonly used in skincare products as well as to make nitroglycerin. But we're going to focus here on these, Because if we started this reaction with a fairly long triglyceride, 12 to 20 carbons, and this is actually something you can pretty easily do, and sometimes when I teach labs for a course like this, we'll actually do this reaction. So we start with Crisco. That's a triglyceride. And then if you have it react with sodium hydroxide, which can be sold sometimes as the compound lye, Lye, you make soap. So how does soap work? So the soap will have a structure something like that. And the specific identity of this chain can vary, but it's basically a long carbon chain with a carboxylate at the end. Well, we know if we try to wash our hands or anything and we have anything greasy on them, that it doesn't work. But the soap molecule has two important aspects to it. It has this long hydrocarbon chain, which is highly nonpolar. It then has this very polar ionic section, highly polar. And so what soap does is that this long carbon chain attracts all of the oils off of whatever you're trying to wash. And then these nonpolar chains will all come together along with the oils that they've trapped. So now water comes along, you're washing your hands, and what does water see? Well, the only thing that water sees are these very, very polar carboxylate groups. And this usually happens in a spherical type of arrangement, where again, these nonpolar parts that don't want anything to do with water stay in the middle, and only these very, very polar parts are out on the surface. We call this a micelle, and that allows the water to wash everything away. The other hydrolysis reaction we want to talk about is amide hydrolysis. Amides are generally much less reactive than esters, so you have to use harsher conditions, but same basic principles apply. So we have an amide here. Add sodium hydroxide and heat to it, and your amide will eventually break apart into the carboxylic acid plus an amine. And amide hydrolysis is highly important because we talked about amidation being how we put amino acids together to form proteins. Amide hydrolysis is how you break them apart. So if we go back up here and grab our dipeptide that we made, dipeptide being a term that refers to having put two amino acids together. What happens if we add sodium hydroxide to it? And maybe some heat. Well, exactly the opposite reaction takes place. This red bond, this is the one that linked the two amino acids together, will now get broken. And so we end up with our carboxylic acid back on one side and our amine back on the other side.